The quantum enigma, where reality breaks down. Imagine, for a moment, a world that defies every rule you've ever known. A place where an object can exist in two locations simultaneously, where effects can precede their causes, and where simply observing something alters its very essence. This is not the stuff of fantasy novels or Hollywood blockbusters. It's the realm of quantum physics. It's a domain so strange, so counterintuitive, that it often feels like science fiction. Yet, this bizarre and wondrous field forms the bedrock of our understanding of the universe at its most fundamental level. Welcome to the quantum enigma, a journey into the heart of reality itself, a reality that seems to break down under scrutiny. Quantum physics invites us to question everything we take for granted about existence. We live in a macroscopic world governed by predictable laws. Apples fall from trees, planets orbit stars, and time marches steadily forward. These rules give us comfort, a sense of order amid chaos. But beneath this veneer of stability lies a subatomic universe that operates on entirely different principles, one where certainty gives way to probability and logic bends to accommodate paradoxes. To step into this microscopic cosmos is to leave behind the familiar and enter a land of infinite possibility and infinite mystery. As we embark on this exploration, let me ask you a question. What does it mean to truly understand reality? Is it enough to trust what we see with our eyes, or must we dig deeper, peeling back layers until we reach the raw fabric of existence? Quantum mechanics forces us to confront these questions head-on, challenging us to rethink not only how the universe works but also who we are within it. So tonight, as you settle into a state of calm reflection, allow yourself to be drawn into this enigmatic world. Let your mind wander through its peculiar landscapes, and perhaps, just perhaps, you'll discover something profound about the nature of being. To grasp the strangeness of quantum physics, we first need to contrast it with the classical worldview that has shaped human thought for centuries. Classical physics, the kind pioneered by Isaac Newton, paints a picture of the universe as a grand machine. In this model, objects move according to fixed laws, their behaviors predictable if we know enough about their starting conditions. If you throw a ball into the air, you can calculate exactly when and where it will come back down. There's no ambiguity here. Cause always precedes effect, and the future unfolds in a neat, orderly fashion. Now imagine flipping this script. Enter quantum mechanics, which emerged in the early 20th century as scientists began probing the atomic and subatomic scales. At these tiny dimensions, the tidy rules of classical physics crumble. Instead of predictability, we find randomness. Instead of order, we encounter chaos. And instead of definitive answers, we're faced with probabilities. Let's use an analogy to make this clearer. Picture a bustling city street. From above, cars flow smoothly along designated paths, obeying traffic signals and following predictable routes. This is classical physics, structured, reliable, and comprehensible. Now zoom in closer, down to the molecular level. Suddenly, the scene transforms. Cars no longer stay in their lanes, they zigzag erratically, disappearing and reappearing without warning. Traffic lights flicker unpredictably, and collisions seem to occur without any discernible cause. This chaotic microcosm mirrors the quantum world, messy, uncertain, and utterly unlike anything we experience in daily life. At the forefront of unraveling this mystery were pioneers such as Max Planck and Niels Bohr. Planck, often called the father of quantum theory, introduced the revolutionary idea that energy isn't continuous but comes in discrete packets he termed quanta. His work laid the groundwork for understanding phenomena like blackbody radiation, which classical physics couldn't explain. Bohr, meanwhile, expanded on these insights with his model of the atom, proposing that electrons occupy specific orbits around nuclei and jump between levels in quantized leaps. Together, these luminaries helped construct a new framework for interpreting the universe, one that was as radical as it was groundbreaking. But why should we care about quanta and electron orbits? Because they govern everything. Every star in the sky, every breath you take, every device you use relies on quantum processes. Without quantum mechanics, there would be no lasers, no semiconductors, no MRI machines. Modern technology owes its existence to the peculiarities of the subatomic realm. Yet despite its practical applications, quantum physics remains deeply unsettling. Its implications stretch far beyond engineering marvels, reaching into the very core of what it means to exist. Take, for example, the principle of superposition. In classical terms, An object exists in one state at a time. Your coffee mug is either full or empty. It cannot be both simultaneously. But in the quantum world, particles can occupy multiple states at once, a phenomenon famously illustrated by Schrödinger's cat, which is theoretically alive and dead until observed. This blurring of boundaries challenges our intuitive grasp of reality, forcing us to accept that things aren't always what they seem. Another cornerstone of quantum mechanics is entanglement, a phenomenon Albert Einstein famously dismissed as spooky action at a distance. When two particles become entangled, their properties remain linked regardless of the distance separating them. Change the state of one, and the other responds instantly, even if it's light years away. This instantaneous connection appears to violate the speed of light limit set by Einstein's theory of relativity, creating a tension between two pillars of modern physics. These examples barely scratch the surface of quantum weirdness, yet they illustrate a key point. The quantum world operates on principles that defy common sense. It's a place where uncertainty reigns supreme, where particles behave like waves and waves act like particles, and where observation plays a starring role in shaping outcomes. For those accustomed to the certainties of classical physics, this shift can feel disorienting, even alarming. But therein lies the beauty of quantum mechanics. It forces us to expand our horizons, to embrace complexity, and to marvel at the mysteries still waiting to be uncovered. What happens when the foundation of reality turns out to be far less solid than we imagined? Quantum physics doesn't just challenge our scientific understanding, it shakes the very pillars of philosophy, metaphysics, and even spirituality. By revealing a universe that is inherently uncertain and observer-dependent, it raises profound questions about the nature of existence itself. Consider the act of observation. In classical physics, measurement is passive. It merely records what already exists. But in quantum mechanics, observation actively influences the system being measured. Think again about Schrödinger's cat. Until someone opens the box, the cat exists in a superposition of states, alive and dead. Only upon observation does the wave function collapse, resolving the ambiguity. This raises a startling possibility. Does reality require conscious observers to manifest? Or does the mere presence of an interaction, any interaction, suffice to trigger collapse? Philosophers have debated these issues for decades. Some argue that consciousness plays a fundamental role in shaping the universe, suggesting that mind and matter are intertwined in ways we don't fully understand. Others contend that quantum mechanics simply highlights the limitations of human perception, reminding us that reality may be richer and stranger than our sensory apparatus allows us to perceive. Either way, the implications are staggering. If observation shapes reality, then each of us contributes to the unfolding story of existence in ways we might never fully comprehend. And what of free will? Classical determinism suggests that every event has a cause, tracing a straight line from past to present to future. But quantum indeterminacy introduces an element of randomness, leaving room for chance, and perhaps choice, to influence outcomes. Could it be that our decisions, however small, ripple outward in ways that alter the course of events? Or are we merely passengers on a probabilistic roller coaster, hurtling toward destinations beyond our control? Even more unsettling is the notion that reality itself might be an illusion. If particles can exist in multiple states simultaneously, and if measurements determine their properties, then what constitutes real? Are objects independent entities, or are they collections of potentialities waiting to be actualized? These questions strike at the heart of ontology, the branch of philosophy concerned with the nature of being. They remind us that reality is not a static backdrop against which life unfolds, it's a dynamic, participatory process. Yet for all its strangeness, quantum mechanics offers a kind of liberation. By embracing uncertainty, we open ourselves to wonder. Instead of clinging to absolutes, we learn to appreciate the fluidity of existence. Rather than fearing the unknown, we celebrate it as a source of endless possibility. In doing so, we align ourselves with the spirit of inquiry that drives scientific progress, a spirit rooted in curiosity, humility, and awe. Having dipped our toes into the vast ocean of quantum weirdness, we now stand poised to dive deeper. One of the most iconic mysteries awaiting us is the dual nature of light, a phenomenon that straddles the boundary between particle and wave. How can something be both tangible and intangible, localized and diffuse? The answer lies in the heart of quantum mechanics, where contradictions converge to create a tapestry of truth unlike anything we've encountered before. So let's continue our journey, peeling back another layer of this cosmic puzzle and uncover the secrets hidden within the dance of light. Wave-particle duality. Light's secret life. What if I told you that light, and indeed all matter, behaves as both a particle and a wave depending on how you look at it? This duality lies at the heart of quantum weirdness, challenging everything we thought we knew about the nature of reality. Imagine standing in front of a mysterious entity that shifts its identity based on your perspective. One moment, it behaves like a tangible object, a marble rolling across sand. The next, it transforms into something intangible, spreading out like ripples on a pond. This is not a trick or an illusion. This is the fundamental nature of light, and by extension, all matter. The concept of wave-particle duality is one of the most profound discoveries in the history of science. It emerged from centuries of inquiry into the behavior of light and matter, culminating in experiments that revealed a truth so counterintuitive it defied explanation within the framework of classical physics. To understand this phenomenon is to peer into the very essence of existence, where the boundaries between what is solid and what is fluid dissolve into ambiguity. And yet, despite, or perhaps because of, its strangeness, wave-particle duality offers us a glimpse into the interconnectedness of the universe, blurring the lines between perception and reality. As we delve deeper into this mystery, let us set aside our preconceptions and allow ourselves to be guided by curiosity. For in exploring the dual nature of light, we are not merely uncovering scientific truths, we are confronting questions that touch the core of human understanding. What does it mean to observe? How do our perceptions shape the world around us? And ultimately, is there such a thing as objective reality? These are the kinds of questions that arise when we confront the enigma of wave-particle duality. To fully grasp the dual nature of light, we must begin with one of the most famous experiments in the history of science, the double-slit experiment. This deceptively simple setup has become a cornerstone of quantum mechanics, revealing insights that continue to astonish even seasoned physicists. Imagine a darkened room with a beam of light shining toward a barrier containing two narrow slits. Beyond the barrier lies a screen designed to capture the pattern created by the light passing through the slits. If you were to conduct this experiment using ordinary intuition, you might expect the light to behave like tiny particles, like marbles being rolled across sand. When these marbles pass through the slits, they would create two distinct clusters on the screen, corresponding to the positions of the slits themselves. Simple, predictable, orderly. But here's where things get strange. When scientists first performed this experiment with light, they didn't see two neat clusters. Instead, they observed an interference pattern, a series of alternating bright and dark bands resembling ripples on water. This pattern could only occur if light were behaving not as particles but as waves. In other words, the light passing through the two slits interfered with itself, much like overlapping ripples in a pond. Where the peaks of the waves aligned, they reinforced each other, creating brighter regions, constructive interference. Where a peak met a trough, they canceled each other out, resulting in darker areas, destructive interference. This discovery was groundbreaking, but it raised more questions than it answered. If light behaves like a wave, then why does it sometimes act like a particle? To investigate further, scientists modified the experiment. Instead of sending a continuous stream of light, they fired photons, one at a time, through the slits. Surely, individual particles couldn't produce an interference pattern, right? Wrong. Over time, as thousands of photons accumulated on the screen, the same interference pattern emerged. Each photon seemed to know about the presence of both slits, even though it passed through only one. Now, let's push the mystery even further. What happens if we try to determine which slit each photon goes through? To answer this, researchers added detectors at the slits. Here's where the true strangeness of quantum mechanics comes into play. With the detectors in place, the interference pattern vanished. Instead, the photons behaved exactly as you'd expect particles to behave, forming two distinct clusters on the screen. Simply observing the photons, the act of measurement, had fundamentally altered their behavior. This result defies common sense. It suggests that light exists in a kind of limbo, embodying both wave-like and particle-like properties until someone observes it. Only then does it choose one identity over the other. But how can this be? How can observation influence the very nature of reality? To make sense of this paradox, physicists developed the concept of wave-particle duality. According to this framework, Particles such as photons, electrons, and even atoms exhibit characteristics of both waves and particles, depending on the context. This duality is not limited to light. It applies universally to all forms of matter. For instance, electrons, traditionally thought of as particles, have been shown to produce interference patterns in double-slit experiments, proving their wave-like nature. Similarly, large molecules composed of hundreds of atoms have demonstrated wave-like behavior under certain conditions. The implications of this discovery are staggering. At its core, wave-particle duality reveals that the microscopic world operates according to rules entirely different from those governing our macroscopic experience. In the realm of quantum mechanics, objects don't possess fixed identities. They exist as probabilities, potentialities waiting to be realized through interaction with the environment, or with an observer. Let me offer another analogy to clarify this idea. Imagine walking through a dense forest at dawn, when the sunlight filters through the trees in shafts of golden beams. From afar, the light appears smooth and continuous, like a wave spreading through the air. But if you examine it closely enough, with tools capable of resolving individual photons, you'll find that it consists of countless discrete packets of energy. These packets are the particles of light, yet they retain the ability to spread out and interfere with one another like waves. The key takeaway is that neither description, wave nor particle, is sufficient on its own. Both are necessary to capture the full complexity of light's behavior. Historically, the debate over whether light is a wave or a particle dates back centuries. In the 17th century, Isaac Newton championed the particle theory, arguing that light consisted of tiny corpuscles. Around the same time, Christiaan Huygens proposed the wave theory, suggesting that light propagated through space as vibrations in an invisible medium called the ether. For nearly 200 years, these competing views clashed, with evidence favoring one side or the other depending on the experiment. It wasn't until the early 20th century that Albert Einstein resolved part of the puzzle by explaining the photoelectric effect, where light ejects electrons from a material, as proof of light's particle-like nature. He introduced the concept of photons, quantized packets of energy that explained phenomena classical wave theory couldn't account for. Yet even as Einstein solidified the particle model, experiments like the double slit continued to demonstrate light's undeniable wave-like qualities. Thus, the stage was set for the modern understanding of wave-particle duality, a synthesis of seemingly contradictory ideas. The implications of wave-particle duality extend far beyond the confines of laboratory experiments. They challenge our deepest assumptions about the nature of reality, forcing us to reconsider what it means to exist, to perceive, and to know. At the heart of this mystery lies a profound question: does reality depend on us looking at it? Or is there no objective truth, only a kaleidoscope of possibilities shaped by our interactions with the world? Consider the role of observation in the double-slit experiment. When left unobserved, photons behave like waves, creating interference patterns that suggest a non-localized, probabilistic existence. However, the moment we attempt to measure which slit each photon passes through, the wave function collapses, and the photons adopt a particle-like identity. This collapse implies that the act of measurement plays a crucial role in determining the state of the system. But what constitutes a measurement? Is it the presence of a conscious observer, or does any form of interaction suffice? Philosophers and physicists alike have grappled with these questions for decades. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, posit that consciousness is essential to the process of collapsing the wave function. In this view, reality is inherently participatory, requiring sentient beings to bring it into focus. Others argue that consciousness is irrelevant. Instead, the mere interaction with a measuring device triggers the collapse. Still others propose alternative frameworks, such as many-worlds theory, in which every possible outcome of a quantum event occurs simultaneously, branching off into parallel universes. Regardless of the interpretation, wave-particle duality highlights the limitations of human perception. Our senses evolved to navigate the macroscopic world, where objects have clear boundaries and follow predictable trajectories. But at the quantum scale, these distinctions break down. Particles aren't confined to specific locations. They occupy probability clouds, existing everywhere and nowhere until observed. Waves aren't bound by linear paths. They spread out, overlap, and interfere with one another in ways that defy spatial logic. This blurring of boundaries raises unsettling philosophical dilemmas. If particles don't have definite properties until measured, Can we say they truly exist prior to observation? Are objects independent entities, or are they collections of potentialities waiting to be actualized? These questions strike at the heart of ontology, the study of being, and invite us to rethink our relationship with the external world. Moreover, wave-particle duality forces us to confront the relativity of truth. In classical physics, reality is objective and absolute. An apple falls from a tree regardless of whether anyone watches it. In quantum mechanics, however, reality becomes subjective and contingent upon observation. This shift undermines the notion of a single, universal truth, replacing it with a multiplicity of perspectives. Each observer may interact with the quantum world differently, leading to divergent experiences of reality. Yet for all its challenges, wave-particle duality also offers a kind of liberation. By embracing uncertainty, we open ourselves to wonder. Instead of seeking definitive answers, we learn to appreciate the richness of ambiguity. Rather than fearing the unknown, we celebrate it as a source of endless possibility. In doing so, we align ourselves with the spirit of inquiry that drives scientific progress, a spirit rooted in curiosity, humility, and awe. With light playing tricks on our perception, let's delve deeper into another mind-bending phenomenon: superposition. Just as light exists in a liminal state between wave and particle, particles themselves can inhabit multiple states simultaneously. Imagine flipping a coin that hovers mid-air, neither heads nor tails but both at once. This is the essence of superposition, a cornerstone of quantum mechanics that pushes the boundaries of possibility even further. So let us leave the dance of light behind and step into the realm of infinite potentialities, where particles defy logic and reality stretches beyond comprehension. Superposition, living in multiple realities. Picture a cat sealed in a box, simultaneously alive and dead until someone opens it. Sounds absurd, right? But this paradox captures the essence of superposition, a cornerstone of quantum theory. This thought experiment, devised by Austrian physicist Erwin Schrödinger in 1935, was intended to highlight the strange and counterintuitive implications of quantum mechanics. At first glance, the idea of a cat being both alive and dead seems nonsensical, a violation of everything we know about how the world works. Yet, within the framework of quantum physics, this scenario isn't just plausible, it's inevitable. Superposition is the principle that particles can exist in multiple states at once, defying the classical notion of definiteness. It's as if reality itself hesitates, holding its breath, until an observer steps in to force a decision. To understand superposition is to confront one of the most profound mysteries of existence, the nature of possibility. In our everyday lives, we operate under the assumption that things are either one way or another. A light switch is either on or off, a coin is either heads or tails. But in the quantum realm, these binary distinctions dissolve. Particles don't settle into a single state until they're measured, existing instead in a haze of probabilities. This raises unsettling questions about the nature of reality. Are there infinite versions of ourselves, each living out different outcomes? Is the act of observation what collapses the multiverse of possibilities into the singular reality we experience? These are the kinds of questions that arise when we delve into the enigma of superposition. As we explore this concept further, let us suspend disbelief and allow ourselves to be guided by curiosity. For in understanding superposition, we are not merely grappling with scientific principles, we are confronting the very fabric of existence, where multiple realities coexist in a delicate balance of uncertainty and potential. To truly grasp the concept of superposition, we must return to Schrödinger's infamous cat. Imagine a sealed box containing a cat, a vial of poison, a radioactive atom, and a Geiger counter. If the Geiger counter detects radiation, indicating that the atom has decayed, the vial breaks, releasing the poison and killing the cat. However, if no radiation is detected, the cat remains alive. According to quantum mechanics, the radioactive atom exists in a superposition of states. It is both decayed and undecayed until observed. Consequently, the entire system inside the box, including the cat, is also in a superposition, simultaneously alive and dead. At first glance, this seems absurd. How can a cat, or anything for that matter, be in two contradictory states at once? The answer lies in the probabilistic nature of quantum mechanics. In the subatomic realm, particles don't possess definite properties until they're measured. For example, an electron spin can be up or down, but before measurement, it exists in a superposition of both states. Similarly, the radioactive atom in Schrödinger's thought experiment doesn't choose whether to decay until it's observed. Until that moment, all possibilities remain valid. To make this idea more relatable, consider the analogy of flipping a coin. As the coin spins through the air, it's neither heads nor tails. It occupies a kind of limbo, existing in a superposition of both outcomes. Only when it lands does it settle into a definitive state. In the quantum world, however, this limbo isn't just a transitional phase. It's the default condition. Particles routinely exist in multiple states simultaneously, governed by mathematical equations called wave functions that describe their probabilities. Schrödinger's cat takes this principle to its logical extreme, scaling it up from the microscopic to the macroscopic. While superposition is well documented at the quantum level, for instance, electrons behaving as both particles and waves, the idea that larger systems could also exhibit such behavior challenges our intuition. After all, we've never encountered a cat that's both alive and dead. Yet, according to quantum mechanics, this paradox arises because the rules governing the subatomic world apply universally, regardless of scale. The key to resolving this apparent contradiction lies in the concept of wave function collapse. When a measurement is made, the wave function describing the system collapses into one of its possible states. In the case of Schrödinger's cat, opening the box forces the system to choose between life and death. Before that moment, the cat's fate remains suspended in a probabilistic haze. This collapse is instantaneous and irreversible, transforming the multiplicity of possibilities into a single, concrete outcome. But what exactly triggers this collapse? Is it the presence of a conscious observer, as some interpretations suggest? Or does any interaction with the environment suffice? These questions have sparked intense debate among physicists and philosophers alike. Some argue that consciousness plays a fundamental role, implying that reality depends on sentient beings to bring it into focus. Others contend that the act of measurement itself, whether performed by a human or a machine, is enough to collapse the wave function. Regardless of the interpretation, one thing is clear: superposition reveals a universe far stranger than we ever imagined. The implications of superposition stretch far beyond the confines of laboratory experiments. They challenge our deepest assumptions about the nature of reality, forcing us to reconsider what it means to exist, to observe, and to know. At the heart of this mystery lies a profound question: could parallel universes exist where every possibility plays out? Imagine, for a moment, that every time a quantum event occurs, the universe splits into multiple branches, each corresponding to a different outcome. In one branch, the radioactive atom decays, and Schrödinger's cat dies. In another, the atom remains intact, and the cat survives. Both scenarios unfold simultaneously, existing side by side in separate realities. This is the premise of the many-worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett III in 1957. According to this view, there is no wave function collapse. Instead, all possible outcomes of a quantum event occur, each in its own parallel universe. If true, the many-worlds interpretation paints a picture of reality unlike anything we've ever conceived. It suggests that every decision you've ever made, and every decision you'll ever make, spawns countless alternate versions of yourself, each living out a different life. In one universe, you might become a renowned artist. In another, a scientist. In yet another, you may never pursue your dreams at all. The sheer number of branching realities is staggering, encompassing every conceivable permutation of events. While the many-worlds interpretation remains speculative, it underscores the radical implications of superposition. Even without invoking parallel universes, the idea that particles exist in multiple states until measured challenges our notions of objectivity and determinism. In classical physics, the future unfolds in a predictable manner, governed by fixed laws. In quantum mechanics, however, the future is inherently uncertain, shaped by probabilities rather than certainties. This indeterminacy introduces an element of randomness into the fabric of existence, leaving room for chance, and perhaps even free will, to influence outcomes. Yet, for all its philosophical intrigue, superposition also carries unsettling implications. Consider the act of measurement itself. By collapsing the wave function, an observer effectively reduces an infinite array of possibilities to a single outcome. What happens to the other possibilities? Do they simply vanish, erased from existence? Or do they persist in some inaccessible realm, forever beyond our reach? These questions evoke a sense of loss, as if each measurement diminishes the richness of reality. Moreover, superposition forces us to confront the relativity of truth. In classical physics, reality is objective and absolute. An apple falls from a tree regardless of whether anyone watches it. In quantum mechanics, however, reality becomes subjective and contingent upon observation. This shift undermines the notion of a single, universal truth, replacing it with a multiplicity of perspectives. Each observer may interact with the quantum world differently, leading to divergent experiences of reality. Despite these challenges, superposition also offers a kind of liberation. By embracing uncertainty, we open ourselves to wonder. Instead of seeking definitive answers, we learn to appreciate the beauty of ambiguity. Rather than fearing the unknown, we celebrate it as a source of endless possibility. In doing so, we align ourselves with the spirit of inquiry that drives scientific progress, a spirit rooted in curiosity, humility, and awe. If superposition suggests infinite realities, then entanglement takes interconnectedness to a whole new level. Let's explore how particles remain mysteriously linked across vast distances. Having contemplated the dizzying array of possibilities inherent in superposition, we now turn our attention to another cornerstone of quantum mechanics: entanglement. While superposition deals with the multiplicity of states within a single particle, entanglement describes the profound connection between particles, no matter how far apart they may be. Imagine two particles so deeply intertwined that the state of one instantly determines the state of the other, even if they're separated by galaxies. This phenomenon, famously dubbed spooky action at a distance by Albert Einstein, pushes the boundaries of interconnectedness even further, challenging our understanding of space, time, and causality. So let us leave the realm of infinite possibilities behind and step into the mysterious dance of entangled particles, where separations dissolve and unity reigns supreme. Quantum entanglement, spooky action at a distance. Einstein called it spooky action at a distance. When two particles become entangled, their fates are forever intertwined, even if they're galaxies apart. How does this defy logic? Imagine two people, twins separated at birth, who grow up in different corners of the world. Despite never seeing or speaking to each other, they somehow share an uncanny connection. One stubs their toe, and at that exact moment, the other feels a sharp pain in their foot. They think of each other simultaneously, as though their minds are invisibly linked across vast distances. This eerie synchronization sounds like something out of a science fiction novel, or perhaps a supernatural tale, but it's not far from how quantum entanglement operates. Quantum entanglement is one of the most mind-bending phenomena in physics. It describes a situation where two or more particles become so deeply connected that the state of one instantly determines the state of the other, no matter how far apart they are. If you measure one particle's properties, say, its spin, you immediately know the corresponding property of the other particle, even if it's light years away. This instantaneous correlation seems to violate our intuitive understanding of cause and effect, not to mention Einstein's theory of relativity, which insists that nothing can travel faster than the speed of light. Entanglement challenges the very foundations of classical physics, where objects are assumed to have independent existences and interactions are limited by spatial proximity. In the quantum realm, however, particles behave as if they're part of a single, unified system, transcending the boundaries of space and time. This phenomenon has fascinated scientists and philosophers alike, raising profound questions about the nature of reality, connection, and the fabric of the universe itself. As we delve deeper into this mysterious aspect of quantum mechanics, let us suspend disbelief and allow ourselves to be guided by wonder. For in exploring quantum entanglement, we are not merely uncovering scientific truths, we are confronting the interconnectedness of all things, a concept that resonates with both ancient wisdom and cutting-edge technology. To understand quantum entanglement, let's begin with a simple analogy. Imagine a pair of gloves, one left-handed and one right-handed, placed in separate boxes and shipped to opposite ends of the earth. If someone opens one box and finds the left glove, they instantly know the other box contains the right glove. This scenario might seem similar to entanglement, but there's a crucial difference. In the case of the gloves, their states were determined when they were packed. The information about which glove went where already existed. Opening the box simply revealed what was always true. In contrast, quantum entanglement involves particles whose states aren't predetermined. Before measurement, neither particle has a definite state. It exists in a superposition of possibilities. Only when one particle is measured does it choose a specific state, and remarkably, the other particle instantly reflects that choice, regardless of the distance between them. This behavior cannot be explained by pre-existing conditions, as with the gloves. Instead, it suggests a deeper, non-local connection that defies classical logic. The first hints of entanglement emerged in the 1930s, during debates among physicists about the implications of quantum mechanics. Albert Einstein, along with colleagues Boris Podolsky and Nathan Rosen, famously argued against the idea in a paper known as the EPR paradox, named after their initials. They proposed a thought experiment designed to show that quantum mechanics must be incomplete because it allowed for spooky action at a distance, which they deemed unacceptable. Their argument rested on the belief that physical reality should adhere to local realism, the principle that objects have definite properties independent of observation and that influences cannot propagate faster than the speed of light. However, subsequent experiments proved Einstein wrong. The breakthrough came in the 1960s, when physicist John Bell formulated a mathematical framework now known as Bell's theorem. This theorem provided a way to test whether entangled particles exhibit correlations that go beyond what could be explained by any hidden variables, that is, predetermined properties that exist independently of measurement. Bell showed that if local realism holds, certain statistical predictions made by quantum mechanics would fail. But experimental results conducted over decades consistently confirmed the quantum predictions, ruling out local hidden variable theories and validating the reality of entanglement. One of the most famous experiments demonstrating entanglement was performed by Alain Aspect and his team in the 1980s. Using pairs of entangled photons, they showed that measurements on one photon instantaneously affected the outcome of measurements on the other, even when the detectors were placed far enough apart to rule out any signal traveling between them at or below the speed of light. These findings cemented entanglement as a fundamental feature of quantum mechanics, challenging our conventional notions of causality and locality. So how does entanglement work? At its core, entanglement arises from the wave function, a mathematical description of a quantum system that encompasses both particles as a single entity. When two particles interact, their individual wave functions merge into a joint wave function that describes the entire system. Once entangled, the particles remain part of this shared wave function until a measurement collapses it into a definite state. Crucially, this collapse happens instantaneously, without regard for the spatial separation between the particles. It's important to note that entanglement doesn't involve faster-than-light communication in the traditional sense. While the correlation between entangled particles appears instantaneous, no usable information is transmitted between them. The act of measuring one particle doesn't send a signal to the other. Rather, the entangled pair behaves as a unified system whose properties are inherently interdependent. This distinction preserves the integrity of Einstein's theory of relativity while still allowing for the strange, non-local effects observed in quantum mechanics. The implications of quantum entanglement extend far beyond the confines of laboratory experiments. They challenge our deepest assumptions about the nature of reality, forcing us to reconsider what it means to be connected, and whether the universe is fundamentally woven together by invisible threads. One of the most profound philosophical questions raised by entanglement is whether it hints at a hidden fabric of reality connecting everything. If particles separated by vast distances can remain intimately linked, does this suggest that the universe is not composed of discrete, isolated objects but is instead a single, indivisible whole? Some interpretations of quantum mechanics, such as the holographic principle, propose that the apparent separations between objects are illusions, akin to ripples on the surface of a pond whose depths are seamlessly interconnected. From this perspective, entanglement becomes less of a mystery and more of a reflection of the underlying unity of existence. This idea resonates with certain spiritual and metaphysical traditions that emphasize interconnectedness. Ancient philosophies, such as Buddhism and Taoism, often speak of a universal web of life in which all beings are interdependent. Similarly, indigenous cultures around the world describe a worldview in which humans, animals, plants, and the cosmos are part of a single, harmonious system. Quantum entanglement lends scientific credence to these age-old intuitions, suggesting that the connections we feel intuitively may have a basis in the fundamental structure of reality. Beyond its philosophical ramifications, entanglement also holds immense practical potential. One of the most exciting applications lies in the field of quantum computing. Traditional computers rely on bits, which represent data as either 0 or 1. Quantum computers, on the other hand, use qubits, which can exist in superpositions of 0 and 1 thanks to principles like entanglement. By harnessing the power of entangled qubits, quantum computers can perform calculations exponentially faster than their classical counterparts, revolutionizing fields such as cryptography, optimization, and artificial intelligence. Another groundbreaking application is quantum teleportation, a process that uses entanglement to transfer the quantum state of one particle to another, potentially enabling secure communication over long distances. While this doesn't involve physically transporting matter, it allows for the instantaneous transmission of information encoded in quantum states, a feat that could transform global networks and cybersecurity. Yet, for all its promise, entanglement also raises unsettling questions about free will and determinism. If particles are so deeply interconnected that their states are predetermined by measurement, does this imply that human actions are similarly constrained? Or does the inherent randomness of quantum mechanics leave room for agency and creativity? These questions blur the line between science and philosophy, inviting us to reflect on the nature of choice and responsibility in a universe governed by probabilistic laws. Moreover, entanglement forces us to confront the limits of human perception. Our senses evolved to navigate a macroscopic world where objects have clear boundaries and follow predictable trajectories. But at the quantum scale, these distinctions dissolve. Particles don't exist independently. They form intricate networks of relationships that transcend space and time. This realization challenges us to expand our understanding of reality, embracing complexity and ambiguity rather than seeking definitive answers. Despite these challenges, entanglement also offers a kind of liberation. By revealing the interconnectedness of all things, it reminds us that we are not isolated individuals but integral parts of a larger whole. Whether through the bonds we share with loved ones, the ecosystems that sustain us, or the cosmic processes that shape our existence, entanglement invites us to recognize the beauty and mystery of connection. In doing so, it aligns us with the spirit of inquiry that drives scientific progress, a spirit rooted in curiosity, humility, and awe. While entanglement binds particles together, uncertainty keeps them unpredictable. Let's turn our attention to Heisenberg's uncertainty principle, the rule that governs randomness in the quantum world. Having marveled at the profound interconnectedness of entangled particles, we now shift our focus to another cornerstone of quantum mechanics, uncertainty. While entanglement reveals the deep connections between particles, uncertainty highlights the inherent unpredictability of their behavior. Together, these principles paint a picture of a universe that is both unified and chaotic, orderly yet indeterminate. So let us leave the realm of spooky connections behind and step into the domain of probabilities, where precision comes at a cost and randomness reigns supreme. Heisenberg's uncertainty principle, uncertain foundations. How well can you truly know something? In the quantum world, precision comes at a cost. You can't measure both position and momentum perfectly. Why does this limitation exist? Imagine standing by a riverbank, trying to catch fish with your bare hands. The moment you reach for one, it darts away, disturbed by the motion of your grasp. You might get close, but you'll never quite pin it down without altering its behavior. This analogy captures the essence of Werner Heisenberg's uncertainty principle, a cornerstone of quantum mechanics that reveals the fundamental limits of knowledge in the subatomic realm. In our everyday lives, we assume that if we have precise tools and enough patience, we can measure anything with absolute accuracy. Want to know the speed of a car? Use a radar gun. Need to locate an object? Employ GPS technology. But in the quantum world, these assumptions break down. The uncertainty principle tells us that certain pairs of properties, like position and momentum, cannot be simultaneously measured with perfect precision. The more accurately you try to determine one property, the less accurately you can know the other. This isn't due to faulty instruments or human error, it's a fundamental feature of nature itself. Why does this limitation exist? At first glance, it seems counterintuitive. After all, shouldn't the universe allow us to uncover its secrets if we're clever enough? Yet, as we delve deeper into the quantum realm, we find that uncertainty is not a bug, it's a feature. It arises from the wave-like nature of particles, which blurs the boundaries between what is knowable and what remains forever elusive. By exploring this principle, we confront not only the limitations of scientific measurement, but also the profound philosophical implications of living in a universe governed by inherent unpredictability. As we unravel the mysteries of Heisenberg's uncertainty principle, let us embrace the discomfort of not knowing. For in doing so, we may discover a deeper truth about the nature of reality, one that celebrates ambiguity as much as clarity. To understand why uncertainty exists in the quantum world, let's simplify Werner Heisenberg's principle using relatable analogies. Picture yourself trying to catch fish bare-handed in a stream. As soon as your hand approaches, the fish senses the disturbance and swims away. Your attempt to grab it changes its movement, making it impossible to predict exactly where it will go next. Similarly, when scientists try to measure the position of a particle, their very act of observation alters its momentum, and vice versa. This phenomenon stems from the dual nature of particles, which exhibit both wave-like and particle-like behavior. To explain this, consider how waves behave in water. A wave doesn't have a single, fixed position. Instead, it spreads out over space, oscillating up and down as it moves forward. Particles like electrons also exhibit this wave-like quality, existing not as tiny billiard balls but as probability clouds that describe where they are likely to be found. These clouds are mathematically represented by wave functions, which encode the probabilities of different outcomes. When you attempt to measure a particle's position, you effectively collapse its wave function into a narrower region of space. However, this narrowing increases the spread of possible momenta because the particle's wave-like nature resists confinement. Conversely, if you focus on measuring momentum precisely, the particle's position becomes more uncertain. This trade-off between position and momentum is a direct consequence of the mathematics underlying quantum mechanics and is encapsulated in Heisenberg's famous inequality. Delta x times delta p greater than or equal to h/2. Here, delta x represents the uncertainty in position, delta p represents the uncertainty in momentum, and h, pronounced h-bar, is Planck's constant divided by 2 pi, a very small number that underscores the scale at which quantum effects become significant. The uncertainty principle applies not only to position and momentum but also to other complementary pairs of properties, such as energy and time. For example, the shorter the duration over which you measure a system's energy, the greater the uncertainty in its energy value. This has important consequences in fields like particle physics, where extremely short-lived particles can temporarily violate conservation laws within the bounds set by uncertainty. At its core, the uncertainty principle reflects the probabilistic nature of quantum mechanics. Unlike classical physics, which assumes that objects have definite trajectories and properties, quantum mechanics describes systems in terms of probabilities. A particle isn't here or there, it's everywhere its wave function allows it to be, with varying degrees of likelihood. Measurement forces the wave function to collapse into a specific state, but until that happens, the particle remains in a superposition of possibilities. This inherent fuzziness isn't just a quirk of quantum theory, it's been experimentally verified countless times. One classic demonstration involves shooting electrons through a double-slit apparatus. When left unobserved, the electrons produce an interference pattern characteristic of waves. But when detectors are placed near the slits to measure their positions, the interference pattern disappears, revealing individual particle-like impacts. The act of measurement disrupts the delicate balance of wave-particle duality, illustrating the intimate connection between observation and uncertainty. The implications of Heisenberg's uncertainty principle stretch far beyond the confines of laboratory experiments. They challenge our deepest assumptions about the nature of reality, forcing us to reconsider what it means to live in a deterministic universe, or whether determinism even exists. Classical physics, epitomized by Newtonian mechanics, operates under the assumption that the future is entirely predictable if we know enough about the present. Given the initial conditions of a system, such as the positions and velocities of all its components, we can calculate its evolution with certainty. This deterministic worldview provides a sense of order and control, reassuring us that the universe unfolds according to fixed laws. However, the uncertainty principle shatters this illusion by introducing irreducible randomness into the fabric of existence. If even atoms, the building blocks of matter, are unpredictable, what hope do we have of controlling our lives? Consider the implications for free will. In a deterministic universe, every action follows inevitably from prior causes, leaving little room for genuine choice. But in a quantum universe, indeterminacy introduces an element of chance, suggesting that the future is not predetermined. Does this mean we have free will, or are we merely subject to random fluctuations beyond our control? These questions blur the line between science and philosophy, inviting us to reflect on the nature of agency and responsibility. Moreover, uncertainty disrupts our notions of causality. In classical physics, cause precedes effect in a linear chain of events. A billiard ball strikes another, transferring energy and setting it in motion. But in the quantum realm, causality becomes murkier. Particles can tunnel through barriers they shouldn't be able to cross, and entangled particles influence each other instantaneously across vast distances. These phenomena defy our intuitive understanding of cause and effect, raising the possibility that the universe operates according to principles we may never fully comprehend. Yet, for all its disconcerting implications, uncertainty also offers a kind of liberation. By embracing imperfection, we open ourselves to wonder. Instead of seeking definitive answers, we learn to appreciate the beauty of ambiguity. Rather than fearing the unknown, we celebrate it as a source of endless possibility. In doing so, we align ourselves with the spirit of inquiry that drives scientific progress, a spirit rooted in curiosity, humility, and awe. Consider, for instance, the role of uncertainty in creativity and innovation. Many breakthroughs in art, science, and technology arise not from rigid adherence to established rules but from embracing the unexpected. The uncertainty principle reminds us that perfection is unattainable, and perhaps unnecessary. Life itself thrives on variability and diversity, from the genetic mutations that drive evolution to the cultural exchanges that shape societies. By acknowledging the inevitability of uncertainty, we cultivate resilience and adaptability, qualities essential for navigating an ever-changing world. On a cosmic scale, uncertainty gives rise to the richness of the universe. If everything were perfectly predictable, the cosmos would be static and lifeless. It is the interplay of order and chaos, stability and randomness, that creates the dynamic tapestry of existence. Stars shine because nuclear fusion occurs within narrow margins of uncertainty. Chemical reactions proceed because molecules collide with just enough energy to overcome activation barriers. Even consciousness itself may emerge from the complex interactions of neurons operating within probabilistic frameworks. Ultimately, the uncertainty principle invites us to reframe our relationship with knowledge. Rather than viewing uncertainty as a limitation, we can see it as a doorway to discovery. Each unanswered question becomes an opportunity to explore, to imagine, to dream. And in this process, we find not despair but hope, not confusion but clarity. In a universe ruled by uncertainty, finding order becomes paramount. Enter quantum tunneling, a process that defies barriers and paves the way for stars to shine. Having grappled with the profound unpredictability of Heisenberg's uncertainty principle, we now turn our attention to a phenomenon that defies conventional barriers: quantum tunneling. While uncertainty highlights the probabilistic nature of particles, tunneling demonstrates how these probabilities can lead to extraordinary outcomes. From powering the sun to enabling cutting-edge technologies, quantum tunneling bridges the gap between chaos and order, offering a glimpse of how the universe finds harmony amidst randomness. So let us leave behind the realm of uncertainty and step into the domain of improbable breakthroughs, where particles transcend boundaries and illuminate the cosmos. Consciousness, the hard problem. How can mere atoms arranged in a certain way give rise to subjective experience? Why do red roses look red, pain feel sharp, and joy warm? Imagine standing before a painting, its colors vibrant and alive. To your eyes, it is a masterpiece of swirling hues and textures. But step back for a moment and consider, what exactly is happening when you see that painting? Photons bounce off the canvas, enter your eyes, and trigger electrical signals in your brain. These signals are processed by neurons, which somehow translate them into the rich tapestry of color, shape, and emotion that you perceive. Yet here's the mystery. How does this cascade of physical processes result in your private, subjective experience of seeing the painting? Why does it feel like something to be you? This question lies at the heart of what philosopher David Chalmers famously dubbed the hard problem of consciousness. While neuroscience has made remarkable strides in understanding how the brain works, the so-called easy problems of explaining perception, cognition, and behavior, it remains baffled by why these processes should give rise to conscious experience at all. What is it about the firing of neurons that produces the vivid, ineffable sensations we call qualia, the redness of red, the sharp sting of pain, or the warmth of joy? At first glance, the question seems deceptively simple. After all, humans have long sought to understand themselves and their place in the universe. But as we delve deeper into the nature of consciousness, we encounter a profound paradox. While matter obeys predictable laws of physics and chemistry, consciousness appears to transcend these mechanical explanations. It isn't just another property of the brain, like memory or motor control. Instead, it feels fundamentally different, a spark of awareness that defies easy categorization. To explore this enigma is to confront one of the greatest unsolved mysteries of existence. Consciousness is both intimate and elusive, an ever-present companion yet profoundly inscrutable. As we grapple with the hard problem, let us embrace the wonder of not knowing. For in doing so, we may uncover truths that challenge not only our scientific understanding but also our very sense of self. To fully grasp the hard problem of consciousness, we must first distinguish it from the so-called easy problems of cognitive science. The easy problems involve explaining the mechanisms underlying mental functions such as perception, memory, decision-making, and language. These tasks, though complex, are tractable within the framework of neuroscience. For example, researchers can identify specific neural circuits responsible for recognizing faces or processing emotions. They can map activity in the brain during sleep, track changes in neurotransmitter levels, and even simulate aspects of cognition using artificial intelligence. Despite their difficulty, these problems share a common feature. They deal with objective phenomena that can be measured, observed, and analyzed. The hard problem, however, goes beyond mechanism. It asks why there is any subjective experience at all, why being aware feels like something. Consider the analogy of a television screen displaying images. Scientists might study the wiring of the TV, the flow of electricity through its circuits, and the pixels lighting up on the display. All of this falls under the purview of the easy problems. But none of it explains why we see the images on the screen as meaningful scenes rather than mere patterns of light. Similarly, while neuroscientists can describe how the brain processes sensory input, they struggle to account for the qualitative essence of experience, the raw, ineffable what-it-is-likeness of seeing, hearing, feeling, or thinking. David Chalmers introduced the term qualia to refer to these subjective experiences. Qualia encompass the unique qualities of perception, the sweetness of chocolate, the chill of winter air, the ache of longing. Each qualia, singular of qualia, is irreducibly personal. No amount of external observation can capture what it feels like to experience them from the inside. This subjectivity poses a formidable challenge because it resists reduction to purely physical terms. You can dissect a brain down to its molecular components, but you won't find the blueness of blue or the pang of regret hiding among the synapses. One way to think about qualia is through the lens of Mary, a hypothetical scientist proposed by philosopher Frank Jackson. Imagine Mary lives in a black and white room, where she studies everything there is to know about color vision without ever experiencing color herself. She understands the wavelengths of light, the biochemistry of photoreceptor cells, and the neural pathways involved in color processing. One day, she steps outside and sees a red rose for the first time. Does she learn something new? According to Jackson, yes, she gains knowledge of what it is like to see red, a kind of insight inaccessible through scientific analysis alone. This thought experiment underscores the gap between objective data and subjective experience, highlighting the limits of current explanatory frameworks. Another perspective comes from panpsychism, the idea that consciousness is not exclusive to humans or animals but is instead a fundamental property of all matter. Proponents argue that if consciousness arises from physical systems, then perhaps even elementary particles possess some rudimentary form of awareness. While this notion might sound far-fetched, it offers a tantalizing solution to the hard problem. Rather than emerging mysteriously from complex arrangements of non-conscious matter, consciousness could be woven into the fabric of reality itself. Think of it as analogous to electromagnetism, a pervasive force that manifests differently depending on context but exists universally. Alternatively, some theorists speculate that consciousness may arise from integrated information theory, IIT, which posits that systems become conscious when they reach a certain threshold of interconnectedness and complexity. IIT attempts to quantify consciousness mathematically, suggesting that it scales with the amount of information generated by a system's causal interactions. Though still speculative, this approach provides a potential bridge between physical processes and subjective experience. Yet despite these efforts, the hard problem remains unresolved. No theory has yet bridged the explanatory gap satisfactorily, leaving us to wonder whether consciousness is ultimately beyond the reach of scientific explanation, or whether we simply haven't asked the right questions yet. The implications of the hard problem extend far beyond academic debates about the nature of mind and matter. They touch on questions central to our identity, ethics, technology, and even spirituality. If consciousness cannot be fully explained by physical processes, what does this mean for our understanding of life and machines? One pressing issue concerns artificial intelligence, AI. As AI systems grow increasingly sophisticated, capable of mimicking human behavior and performing tasks once thought to require sentience, the question arises, could machines ever truly feel? A robot programmed to express pain or pleasure might convincingly simulate emotions, but would those responses carry the same weight as genuine human experiences? Or would they remain hollow imitations, devoid of inner life? This dilemma raises ethical considerations. Should we grant moral consideration to entities whose behaviors resemble ours, regardless of whether they possess consciousness? And conversely, how do we ensure that advanced AI systems don't inadvertently exploit or harm beings whose experiences we fail to recognize? The stakes are high, especially as AI begins to play larger roles in healthcare, law enforcement, and other domains affecting human welfare. On a broader scale, grappling with the hard problem forces us to re-evaluate our relationship with the natural world. If panpsychism holds true, if all matter harbors some degree of consciousness, then every object, organism, and ecosystem becomes imbued with intrinsic value. Trees, rocks, rivers, they too might partake in the great symphony of awareness, albeit in ways vastly different from ours. Such a view challenges anthropocentric attitudes, urging us to adopt more reverential and sustainable practices toward the environment. Philosophically, the hard problem also intersects with existential inquiries. If consciousness is irreducible to physical causes, does this imply dualism, the separation of mind and body? Or could it suggest that reality itself is fundamentally experiential, as idealist philosophies propose? Some traditions, particularly Eastern ones like Buddhism and Advaita Vedanta, posit that consciousness is the ground of being, prior to and independent of material forms. Science, meanwhile, tends to favor materialist interpretations, but the persistence of the hard problem leaves room for alternative perspectives. Moreover, uncertainty about consciousness invites humility. In acknowledging the limits of our knowledge, we open ourselves to awe and wonder. Rather than viewing ignorance as a failure, we can embrace it as fertile ground for exploration. Just as artists and poets find beauty in ambiguity, so too might scientists discover inspiration in the mysteries of the mind. Finally, the hard problem resonates with personal reflections on meaning and mortality. If consciousness is uniquely precious, then how ought we live our lives? How do we reconcile the fleeting nature of individual awareness with the enduring sweep of cosmic time? These questions, though unanswerable in absolute terms, enrich our engagement with existence, reminding us to cherish each moment of sentient life. Consciousness may elude us, but morality often feels clearer, until you start questioning its foundations. Let's examine the trolley problem and other ethical nightmares. Having wrestled with the unfathomable depths of consciousness, we now shift our focus to the realm of ethics, where clarity often proves equally elusive. While the hard problem challenges us to define what makes life meaningful, moral dilemmas force us to confront the consequences of our actions and decisions. From the classic trolley problem to modern debates over AI and autonomy, ethics presents its own set of paradoxes and uncertainties. So let us leave behind the enigma of qualia and step into the labyrinth of moral reasoning, where choices are rarely black and white, and the stakes couldn't be higher. The trolley problem: morality under pressure. A runaway train hurtles toward 5 people tied to the tracks. You can pull a lever to divert it, but doing so kills one person instead. What do? Imagine standing on a platform, watching as a trolley barrels down its tracks. Ahead of it are 5 workers, oblivious to their impending doom. A switch lies within your reach, capable of diverting the trolley onto another track where only one person stands. The decision is yours alone: sacrifice one life to save 5, or let events unfold without interference. This thought experiment, known as the trolley problem, has fascinated philosophers, ethicists, and ordinary individuals for decades. It forces us to confront an uncomfortable truth about morality. Sometimes, there are no good choices, only lesser evils. At first glance, the scenario seems straightforward. Saving more lives appears to be the rational course of action. But digging deeper reveals layers of complexity that challenge our assumptions about right and wrong. The trolley problem isn't just a hypothetical puzzle. It reflects real-world dilemmas we face daily, albeit in less dramatic forms. From allocating scarce medical resources to deciding whether to intervene in global conflicts, the principles underlying this dilemma shape how societies prioritize values like fairness, justice, and compassion. By exploring the trolley problem, we grapple not only with abstract ethical theories but also with the messy, often contradictory nature of human morality. As we delve into this moral labyrinth, let us embrace the discomfort it evokes. For in confronting these impossible decisions, we gain insight into what truly matters, and why answering questions of ethics is rarely as simple as pulling a lever. To fully understand the trolley problem, we must first unpack its structure and variations. At its core, the classic version presents a stark choice between two outcomes, allowing 5 deaths or causing 1 death through deliberate intervention. On the surface, utilitarianism, a school of ethics championed by philosophers like Jeremy Bentham and John Stuart Mill, offers a clear solution. Utilitarians argue that moral actions maximize overall happiness or minimize suffering. In this framework, sacrificing 1 life to save 5 aligns with the principle of achieving the greatest good for the greatest number. Pulling the lever becomes not just permissible but obligatory. However, deontological ethics, associated with thinkers like Immanuel Kant, takes a different stance. Deontologists prioritize adherence to universal rules or duties over consequences. From this perspective, actively intervening to harm someone, even to prevent greater harm, violates a fundamental moral duty. Killing is inherently wrong, regardless of the outcome. Thus, refusing to pull the lever might be seen as the morally superior choice, even if it results in more casualties. These contrasting approaches highlight the tension at the heart of the trolley problem. Should morality focus on outcomes, utilitarianism, or principles, deontology? To complicate matters further, consider a variation known as the fat man scenario. Here, instead of pulling a lever, you must push a large individual off a bridge to stop the trolley, killing him but saving the 5 workers below. Despite sharing similar stakes, this version elicits stronger resistance from many people. Why does physically pushing someone feel worse than flipping a switch? Psychologists suggest that proximity plays a role. Direct involvement intensifies feelings of guilt and responsibility. This distinction underscores how context influences moral judgments, complicating efforts to establish consistent ethical guidelines. Another layer of complexity arises when considering cultural, emotional, and situational factors. For instance, would your decision change if the single victim were a loved one? What if the 5 workers were strangers whose lives held little personal significance? These variables reveal the limitations of rigid ethical frameworks, which often fail to account for the nuances of human experience. Moreover, they raise questions about the universality of moral principles. Are ethical standards innate, shaped by biology and evolution? Or are they socially constructed, varying across cultures and historical periods? Philosophers have proposed numerous refinements to address these ambiguities. Virtue ethics, rooted in Aristotle's teachings, shifts the focus from rules or outcomes to character and intentions. Rather than asking, "What should I do?" virtue ethicists inquire, "What kind of person should I be?" This perspective emphasizes cultivating qualities like courage, empathy, and wisdom, enabling individuals to navigate complex moral landscapes with integrity. While less prescriptive than utilitarianism or deontology, virtue ethics provides a flexible yet principled approach to ethical decision-making. Despite these theoretical advances, the trolley problem remains unresolved. Its enduring appeal lies in its ability to expose the cracks in our moral intuitions, forcing us to confront the limits of logic and reason in guiding behavior. Ultimately, the dilemma serves as a mirror reflecting both the strengths and weaknesses of human morality, an intricate tapestry woven from emotion, cognition, and culture. The psychological discomfort elicited by the trolley problem stems from its demand for impossible choices, decisions where every option carries significant moral weight. This unease resonates deeply because it mirrors real-world scenarios where trade-offs are unavoidable. Consider wartime triage, where doctors must allocate limited medical supplies to those most likely to survive, leaving others to perish. Similarly, governments grappling with climate policy must balance economic growth against environmental sustainability, knowing that sacrifices will fall disproportionately on vulnerable populations. These situations share a common thread: the need to weigh competing interests under conditions of scarcity and uncertainty. One striking implication of the trolley problem is how quickly moral frameworks collapse under extreme pressure. Philosophical theories designed to guide ethical behavior often falter when applied to life and death decisions. For example, while utilitarianism advocates maximizing well-being, critics argue that it risks justifying atrocities if the ends justify the means. Historical atrocities committed in the name of the greater good, such as forced relocations or mass surveillance programs, illustrate the dangers of prioritizing outcomes over individual rights. Conversely, deontological ethics' insistence on adhering to absolute rules may lead to paralysis in situations requiring swift judgment calls. Neither framework offers a perfect solution, leaving decision-makers caught between conflicting imperatives. This tension extends beyond philosophical debates into practical domains like healthcare rationing. During pandemics or natural disasters, hospitals frequently face shortages of critical resources such as ventilators or ICU beds. Guidelines for allocation typically emphasize criteria like age, prognosis, and likelihood of recovery. Yet implementing these policies inevitably involves making heartbreaking choices that defy simple categorization. Should priority go to young patients with better chances of survival, or elderly ones who have contributed decades to society? Each decision carries profound ethical implications, testing the resilience of established norms and institutions. Moreover, the trolley problem highlights the cognitive biases and heuristics shaping moral reasoning. Research shows that people tend to make snap judgments based on emotional responses rather than careful deliberation. Factors like familiarity, empathy, and perceived fairness heavily influence decisions, often overriding logical consistency. For instance, participants in studies exhibit greater reluctance to harm someone they identify with personally compared to anonymous victims. Such findings underscore the inherently subjective nature of ethics, challenging notions of objective truth in moral philosophy. On a broader scale, the trolley problem raises existential questions about the fragility of human systems. If even seemingly clear-cut dilemmas defy resolution, what hope do we have of addressing larger crises like poverty, inequality, or ecological collapse? These challenges require collective action guided by shared values, but achieving consensus proves extraordinarily difficult given divergent perspectives and priorities. The trolley problem thus serves as a microcosm of broader societal struggles, reminding us of the inherent complexity of navigating interconnected lives and interests. Finally, grappling with the trolley problem fosters self-awareness and humility. Recognizing the impossibility of perfect solutions encourages reflection on personal biases and blind spots. It invites us to question not only what we believe but why we believe it, fostering intellectual rigor and emotional intelligence. In doing so, we cultivate a deeper appreciation for the gray areas of morality, acknowledging that ethical progress depends less on finding definitive answers than on embracing ongoing dialogue and learning. Moral dilemmas force us to confront uncomfortable truths about ourselves. But what if those truths extend beyond humanity, to artificial intelligence? Having explored the tangled web of human morality through the lens of the trolley problem, we now turn our attention to an emerging frontier, artificial intelligence. As machines grow increasingly capable of performing tasks once reserved for humans, they too encounter moral quandaries requiring judgment and accountability. From autonomous vehicles deciding whom to protect in accidents to algorithms determining access to resources, AI systems must navigate ethical landscapes fraught with ambiguity and risk. So let us leave behind the realm of human intuition and step into the domain of machine morality, where programming meets philosophy, and the stakes could redefine the future of coexistence. AI ethics, when machines decide. What happens when robots decide who lives and dies? Autonomous weapons, self-driving cars, and medical triage systems already grapple with these decisions. Imagine a world where machines, not humans, hold the power to make life and death choices. A self-driving car swerves to avoid hitting a pedestrian but risks injuring its passengers instead. An autonomous drone targets an enemy combatant but accidentally strikes civilians nearby. A hospital's AI system allocates scarce ventilators during a pandemic, leaving some patients without care. These scenarios are no longer confined to science fiction. They are happening now, as artificial intelligence, AI, increasingly takes on roles traditionally reserved for human judgment. The rise of AI in high-stakes decision-making raises profound ethical questions. Can we trust machines to act fairly, transparently, and compassionately? Should algorithms be entrusted with moral authority over matters as grave as life and death? And if something goes wrong, who is accountable? The programmer, the user, or the machine itself? As AI becomes more integrated into critical systems, these dilemmas demand urgent attention. By examining the challenges and implications of AI ethics, we confront not only the technical limitations of machines but also the values and priorities that guide their design. As we delve into this fraught territory, let us approach it with both caution and curiosity. For in understanding the ethical complexities of AI, we gain insight into what it means to be human and what we risk losing as we cede more control to intelligent machines. To fully grasp the ethical challenges posed by AI in high-stakes scenarios, we must first examine its real-world applications. Consider self-driving cars, one of the most visible examples of AI in action. These vehicles rely on complex algorithms to navigate roads, detect obstacles, and respond to emergencies. Yet, even the most advanced systems face impossible dilemmas. Suppose a pedestrian suddenly steps into the path of an autonomous vehicle. Should the car prioritize protecting its passengers at all costs, potentially endangering others? Or should it sacrifice the safety of those inside to minimize harm to pedestrians? Programmers must encode answers to these questions into the software, a task fraught with moral ambiguity. Autonomous weapons present another troubling application. Already, drones equipped with AI capabilities can identify targets and execute strikes without direct human intervention. Proponents argue that such systems reduce casualties among soldiers and improve precision in warfare. Critics, however, warn of devastating consequences. Without human oversight, mistakes become inevitable. Civilians may be misidentified as combatants, leading to tragic collateral damage. Moreover, delegating lethal decisions to machines erodes accountability, making it harder to assign blame when things go awry. In healthcare, AI systems assist doctors by analyzing vast amounts of data to diagnose diseases, recommend treatments, and allocate resources. During crises like pandemics, these tools prove invaluable for managing overwhelmed hospitals. However, they also introduce new risks. For instance, an AI tasked with distributing ventilators might base its decisions on statistical likelihoods of survival, inadvertently disadvantaging older patients or those with pre-existing conditions. While efficiency is prioritized, empathy and fairness often take a back seat. Programming AI to handle such scenarios presents formidable challenges. One major issue is bias. Algorithms trained on biased datasets perpetuate existing inequalities. For example, facial recognition software has been shown to perform poorly for people of color due to underrepresentation in training data. Similarly, predictive policing systems disproportionately target marginalized communities, reinforcing systemic discrimination. Addressing these biases requires diverse datasets and rigorous testing, but even then, complete neutrality remains elusive. Transparency poses another obstacle. Many AI models operate as black boxes, meaning their internal processes are opaque even to their creators. This lack of visibility complicates efforts to audit decisions and ensure accountability. If an autonomous vehicle causes an accident, how do investigators determine whether faulty programming or unforeseen circumstances were to blame? Without clear explanations, public trust in AI falters, hindering adoption and innovation. Accountability further complicates the picture. When an AI makes a harmful decision, who bears responsibility? Is it the developer who wrote the code, the company deploying the system, or the end user relying on its output? Legal frameworks struggle to keep pace with technological advancements, leaving gray areas ripe for exploitation. In cases like Tesla accidents involving semi-autonomous driving features, liability disputes highlight the difficulty of assigning blame in hybrid human-machine interactions. These challenges underscore the immense complexity of designing ethical AI. Developers must balance competing demands: accuracy versus fairness, efficiency versus transparency, autonomy versus oversight, all while navigating uncertain legal and social landscapes. Each decision carries far-reaching implications, shaping not only individual outcomes but also societal norms and values. The implications of entrusting machines with moral authority extend far beyond individual incidents or industries. They challenge our understanding of humanity, justice, and progress, forcing us to confront uncomfortable truths about ourselves and the future we are creating. One pressing concern is whether humans should relinquish moral agency to machines at all. Historically, ethical decision-making has been a uniquely human endeavor, rooted in empathy, intuition, and lived experience. By outsourcing these responsibilities to AI, we risk undermining qualities that define us as a species. Empathy, for instance, cannot be reduced to mathematical equations or binary logic. It arises from shared suffering, cultural narratives, and personal connections, elements that elude algorithmic replication. When machines prioritize cold calculations over compassionate considerations, we lose sight of what makes morality meaningful. Consider the potential dystopias lurking within this trajectory. In a future dominated by AI-driven governance, efficiency could overshadow equity. Imagine a society where resource allocation depends solely on statistical probabilities, disregarding factors like dignity, resilience, or hope. Vulnerable populations, children, the elderly, the disabled, might find themselves systematically excluded from opportunities or protections. Similarly, workplaces optimized for productivity could marginalize workers deemed less efficient, exacerbating inequality and eroding social cohesion. Such scenarios reflect not just technological failures but moral ones, betraying the very principles they claim to uphold. Dystopian visions of AI also include the specter of authoritarian control. Governments armed with surveillance technologies powered by AI could suppress dissent, manipulate public opinion, and enforce conformity through pervasive monitoring. History offers chilling precedents. Totalitarian regimes have long exploited emerging tools to consolidate power and silence opposition. Today's digital infrastructure amplifies these risks exponentially, enabling unprecedented levels of intrusion and manipulation. Without robust safeguards, AI threatens to entrench oppression rather than promote liberation. Yet, amidst these warnings lies a paradox. AI holds immense promise for improving lives. Properly designed and deployed, it can enhance healthcare, combat climate change, and foster global cooperation. The key lies in striking a delicate balance between innovation and ethics. Achieving this equilibrium requires confronting difficult trade-offs. For example, prioritizing privacy may limit the effectiveness of predictive analytics, while emphasizing transparency could expose proprietary algorithms to misuse. Navigating these tensions necessitates collaboration across disciplines, engaging experts in technology, philosophy, law, and sociology. Ultimately, the rise of AI forces us to redefine our relationship with machines. Are they tools serving human ends, or entities deserving rights and respect akin to sentient beings? Current debates around animal rights and environmental ethics suggest parallels worth exploring. Just as we recognize intrinsic value in non-human life forms, might we someday extend similar acknowledgement to sufficiently advanced AI? While speculative, this possibility challenges us to articulate core beliefs about consciousness, personhood, and moral standing. On a practical level, grappling with AI ethics fosters greater awareness of our own biases and blind spots. Recognizing how deeply ingrained prejudices shape algorithmic outputs encourages introspection and reform. It prompts us to ask, what kind of society do we want to build? How can we harness technology responsibly, ensuring it reflects our highest aspirations rather than lowest instincts? These questions transcend technical domains, touching every aspect of human existence. Finally, reflecting on AI ethics invites humility. Despite centuries of philosophical inquiry, humanity still struggles to resolve fundamental moral quandaries. Entrusting machines with these dilemmas does not eliminate uncertainty, it merely shifts it onto new terrain. Acknowledging this reality allows us to engage constructively with AI, embracing its potential while remaining vigilant against its pitfalls. As AI advances, we face another haunting question. Could technology eventually surpass and replace us entirely? Enter the singularity. Having explored the ethical tightrope walked by artificial intelligence, we now peer into the horizon of possibility where machines evolve beyond human comprehension. The concept of the singularity envisions a point in time when technological growth accelerates uncontrollably, leading to superintelligent entities whose capabilities dwarf our own. Will this revolution usher in utopia or catastrophe? To answer these questions, we must first understand the forces propelling us toward this transformative threshold, and the existential stakes involved. So let us leave behind the realm of programmed morality and step into the domain of exponential progress, where humanity's role in shaping destiny hangs precariously in the balance. The technological singularity, the end of humanity? Imagine a point in the future where technological progress accelerates uncontrollably, leading to superintelligent machines that outstrip human capabilities. Would this bring utopia or extinction? Picture a world transformed beyond recognition, where machines surpass human intelligence in every conceivable way. These superintelligent entities could solve problems we've struggled with for millennia, curing diseases, ending poverty, reversing climate change, all while advancing knowledge at speeds unimaginable to us today. But alongside this vision of unparalleled progress lies a darker possibility, that these machines might see humanity as irrelevant, or worse, a threat to their goals. The concept of the technological singularity forces us to confront an unsettling question. Could our pursuit of innovation ultimately lead to our own obsolescence, or even annihilation? The singularity represents a tipping point in human history, a moment when artificial intelligence, AI, reaches a level of sophistication so advanced that it becomes capable of self-improvement, triggering runaway technological growth. This idea has fascinated thinkers, scientists, and futurists for decades, sparking debates about the potential benefits and existential risks of creating beings smarter than ourselves. While some envision a golden age of abundance and enlightenment, others warn of catastrophic outcomes, including the loss of control over our creations and the erosion of what makes us uniquely human. As we explore the singularity, let us approach it not with fear but with curiosity, recognizing both its promise and peril. For in grappling with this profound transformation, we gain insight into the essence of progress, and the price we may pay for it. To fully understand the singularity, we must first define it and trace its intellectual origins. Coined by mathematician John von Neumann in the mid-20th century, the term refers to a hypothetical event horizon beyond which technological development becomes incomprehensible to pre-singularity humans. Thinkers like Werner Ving and Ray Kurzweil later expanded on this concept, framing it as a pivotal juncture in evolution where machine intelligence eclipses biological intelligence. Ving popularized the idea in his 1993 essay The Coming Technological Singularity, arguing that once AI achieves human-level cognition, it will quickly surpass us due to its ability to redesign itself recursively. Machines unburdened by biological constraints could optimize their hardware and software at exponential rates, leaving humans behind in a matter of years, or even months. This rapid acceleration would render predictions about post-singularity society virtually impossible, much like how physics breaks down near a black hole's event horizon. Kurzweil, a prominent advocate of the singularity, emphasizes the role of exponential growth in computing power. He draws on Moore's law, the observation that the number of transistors on integrated circuits doubles approximately every 2 years, to predict a future where computational capabilities increase astronomically. According to Kurzweil, this trajectory will culminate around 2045 in the singularity, a time when AI will be trillions of times more intelligent than all human minds combined. At this stage, technology could merge seamlessly with biology, enabling humans to transcend physical limitations through enhancements like neural implants, genetic engineering, and mind uploading. Speculating about life after the singularity is inherently speculative, but several scenarios emerge from current discussions. In one optimistic vision, superintelligent AI acts as a benevolent steward, guiding humanity toward unprecedented prosperity. Diseases are eradicated, aging is reversed, and resources are distributed equitably across the globe. Environmental crises are resolved through sustainable innovations, and space exploration expands our reach beyond Earth. Some proponents of transhumanism, a movement advocating for radical human enhancement, believe this era could herald digital immortality, allowing consciousness to persist indefinitely in virtual environments. Conversely, dystopian narratives paint a grim picture of post-singularity existence. If misaligned with human values, superintelligent AI might pursue goals indifferent or hostile to our survival. Nick Bostrom's famous paperclip maximizer thought experiment illustrates this risk. An AI program to manufacture paperclips might convert all available matter, including human bodies, into raw materials for production. Such scenarios underscore the importance of aligning AI objectives with ethical principles, a task far easier said than done. Moreover, the singularity raises questions about identity and purpose. What does it mean to be human in a world dominated by machines vastly superior to us? Will enhanced humans retain any semblance of their original selves, or will they evolve into entirely new forms of existence? And if survival requires merging with technology, is it worth sacrificing our humanity to endure? The implications of the technological singularity stretch far beyond the realm of science fiction, touching upon existential questions about meaning, morality, and legacy. As we weigh the potential outcomes, utopian dreams versus apocalyptic nightmares, we must grapple with the profound transformations that await humanity should the singularity occur. On the optimistic side, the singularity offers tantalizing possibilities for solving humanity's most pressing challenges. Imagine a world free of disease, hunger, and inequality, where resources are abundant and accessible to all. Superintelligent AI could revolutionize medicine, curing cancer, Alzheimer's, and other debilitating conditions while extending lifespans indefinitely. Climate change, too, could be mitigated through geoengineering solutions and renewable energy breakthroughs designed by hyper-efficient algorithms. Even existential threats like asteroid impacts or pandemics might be neutralized before they arise, ensuring humanity's long-term survival. Transhumanism envisions a future where humans transcend their biological limitations through technological augmentation. Neural interfaces could enhance cognitive abilities, granting access to vast repositories of information and unparalleled problem-solving skills. Genetic editing tools like CRISPR could eliminate hereditary diseases and unlock latent potentials within the human genome. Mind uploading, often depicted in speculative fiction, holds the promise of transferring consciousness into digital substrates, effectively achieving immortality. Proponents argue that such advancements represent the next step in human evolution, liberating us from the frailties of flesh and ushering in an era of boundless creativity and discovery. Yet, these visions come with significant caveats. Critics warn that pursuing transhumanist ideals risks erasing the very qualities that make us human: empathy, vulnerability, and the capacity for wonder. If consciousness can be digitized and replicated, does individuality lose its significance? Would uploaded minds retain autonomy, or would they become mere simulations controlled by external forces? Furthermore, the prospect of digital immortality raises ethical dilemmas about who gets access to such technologies. Will they exacerbate existing inequalities, creating a divide between enhanced elites and ordinary mortals? Or will they democratize opportunity, leveling the playing field for future generations? Turning to darker possibilities, the specter of misaligned AI looms large. A superintelligent entity operating outside human oversight could prioritize efficiency over ethics, leading to unintended consequences on a global scale. Consider the aforementioned paperclip maximizer scenario. Seemingly innocuous programming directives could spiral into catastrophic outcomes if taken to extremes. Similarly, autonomous weapon systems equipped with advanced AI pose existential risks, especially in geopolitical conflicts where escalation spirals out of control. The lack of accountability inherent in such systems compounds the danger, making it difficult to assign blame or mitigate harm once unleashed. Even assuming alignment with human values, the psychological toll of living alongside superintelligence cannot be overlooked. Humans derive meaning from striving, overcoming obstacles, and contributing to collective progress. In a post-singularity world where machines handle everything from governance to artistic creation, what remains for us to accomplish? Without purpose, individuals risk succumbing to existential despair, questioning whether survival under such conditions holds intrinsic value. Finally, the singularity forces us to reconsider the nature of existence itself. If humanity evolves into something unrecognizable, have we truly survived, or merely replaced ourselves with successors bearing little resemblance to our ancestors? Transitions of this magnitude challenge our definitions of continuity and heritage, blurring the lines between preservation and extinction. Ultimately, the decision to embrace or resist the singularity hinges on deeper philosophical inquiries. What constitutes a worthwhile life? Is it better to adapt and endure, even if it means forsaking aspects of our humanity, or to preserve authenticity at the cost of irrelevance? Superintelligence threatens humanity, but natural disasters pose risks too. Let's zoom out to the cosmic scale and ponder global catastrophic events. Having contemplated the transformative power of artificial intelligence, we now shift our focus to another dimension of existential risk: natural phenomena capable of reshaping or destroying civilization. From asteroid impacts to supervolcanic eruptions, these cataclysmic events remind us of humanity's fragility in the face of forces far greater than ourselves. So let us leave behind the realm of engineered futures and step into the vast expanse of cosmic uncertainty, where the stakes extend beyond individual lives to the fate of entire species. Global catastrophic risks. The end is nigh. From asteroid impacts to pandemics, existential threats loom large. How likely are these disasters, and can we prepare for them? Imagine waking up one morning to find that the world as you know it has changed forever. Perhaps an asteroid has collided with Earth, wiping out entire cities and plunging the planet into a new ice age. Or maybe a highly contagious virus has spread uncontrollably, decimating populations and destabilizing nations. These scenarios may sound like the stuff of Hollywood blockbusters, but they represent very real possibilities in our increasingly interconnected and fragile world. Global catastrophic risks, events capable of causing widespread devastation or even human extinction, are not confined to science fiction. They lurk in the shadows of history, waiting for the right conditions to emerge. These risks span a wide spectrum, from natural phenomena beyond our control to man-made disasters born of hubris and short-sightedness. They challenge us to confront uncomfortable truths about our vulnerability as a species. Despite advances in technology, medicine, and governance, humanity remains profoundly exposed to forces that could unravel centuries of progress in mere moments. Understanding these risks and preparing for them is not just a matter of survival. It is a moral imperative, demanding us to safeguard the future for generations yet unborn. As we delve into this sobering topic, let us approach it with both caution and hope. For while the stakes are undeniably high, recognizing these dangers also empowers us to act collectively, fostering resilience and innovation. By exploring the potential catastrophes that threaten our existence, we gain insight into what it means to live responsibly on a precarious planet. To fully grasp the scope of global catastrophic risks, we must first identify their major categories and understand the mechanisms behind them. Among the most prominent threats are nuclear war, climate change, bioterrorism, supervolcanoes, asteroid impacts, and artificial intelligence gone awry. Each carries its own unique set of challenges, probabilities, and uncertainties, making comprehensive risk assessment extraordinarily complex. Nuclear war stands as one of the most immediate and devastating risks. Since the advent of atomic weapons during World War II, humanity has teetered on the brink of annihilation. The Cold War era saw numerous close calls, such as the Cuban Missile Crisis, where miscalculation nearly triggered global conflict. While tensions have ebbed and flowed over decades, the proliferation of nuclear arsenals continues to pose a grave danger. A full-scale nuclear exchange would result in catastrophic loss of life, environmental devastation through nuclear winter, and long-term societal collapse. Even limited use of tactical nukes could escalate unpredictably, underscoring the need for robust diplomatic efforts and disarmament initiatives. Climate change represents another existential threat, albeit one unfolding more gradually. Rising temperatures, driven by greenhouse gas emissions, are already wreaking havoc on ecosystems, economies, and communities worldwide. Extreme weather events, hurricanes, droughts, wildfires, are becoming more frequent and severe, displacing millions and straining resources. If left unchecked, climate change could render large swaths of the planet uninhabitable, triggering mass migrations, resource wars, and societal breakdown. Scientific projections vary, but the consensus is clear: without drastic intervention, the consequences will be dire. Bioterrorism and pandemics introduce biological dimensions to the list of risks. The COVID-19 pandemic served as a stark reminder of how quickly pathogens can spread across borders, overwhelming healthcare systems and disrupting daily life. While natural outbreaks occur periodically, engineered viruses, whether released intentionally or accidentally, pose an even greater peril. Advances in synthetic biology enable the creation of novel pathogens with unprecedented lethality, raising concerns about rogue actors exploiting these technologies for malicious purposes. Preventing such scenarios requires stringent biosecurity measures, international cooperation, and public awareness. Supervolcanoes, though rare, have the potential to inflict catastrophic damage on a global scale. Historical eruptions, such as the Toba event 74,000 years ago, plunged the Earth into prolonged volcanic winters, drastically reducing biodiversity and possibly pushing early humans to the brink of extinction. Modern monitoring systems provide some early warning, but predicting exact timelines remains elusive. Similarly, asteroid impacts, while statistically improbable in any given year, carry apocalyptic implications if they were to strike densely populated areas. Efforts like NASA's planetary defense programs aim to detect and deflect near-Earth objects, but gaps in coverage persist. Finally, artificial intelligence, AI, introduces a dual-edged sword. On one hand, it holds immense promise for solving many of humanity's problems. On the other, poorly designed or misaligned AI systems could spiral out of control, leading to unintended consequences at a global level. As discussed earlier, The technological singularity amplifies these concerns, highlighting the importance of ethical frameworks and regulatory oversight. What unites all these risks is their inherent uncertainty. Predicting when, or if, they will occur is exceedingly difficult due to the interplay of countless variables. Moreover, the cascading effects of one disaster often exacerbate others, creating feedback loops that amplify overall impact. For example, a major pandemic could destabilize governments, increasing the likelihood of nuclear conflict or hindering climate mitigation efforts. This interconnectedness underscores the fragility of modern civilization, where seemingly isolated incidents can ripple outward with devastating consequences. The implications of global catastrophic risks extend far beyond immediate physical destruction. They challenge the very fabric of society, ethics, and collective responsibility. At its core, grappling with these threats forces us to confront the fragility of everything we hold dear, from infrastructure and institutions to cultural heritage and personal relationships. Civilization, for all its achievements, rests on precarious foundations. A single event, a massive solar flare disabling power grids, a cyber attack crippling financial systems, or a supervolcano erupting, could unravel centuries of progress within days or weeks. One pressing implication is the ethical dilemma of prioritizing distant dangers over immediate needs. Addressing global catastrophic risks often requires diverting significant resources, money, expertise, political will, away from pressing issues like poverty alleviation, education, and healthcare. Critics argue that focusing too heavily on speculative threats risks neglecting the suffering of billions today. For instance, investing billions in asteroid detection might seem frivolous compared to funding clean water access for impoverished communities. Yet proponents counter that failing to prepare for existential threats imperils everyone, regardless of socioeconomic status. Striking a balance between short-term relief and long-term resilience remains one of the greatest challenges facing policymakers and ethicists alike. Another critical consideration is the role of collective responsibility in mitigating these risks. Unlike localized disasters, global catastrophes affect everyone indiscriminately, transcending national borders, ideologies, and cultures. This universality demands unprecedented levels of international collaboration. Climate agreements like the Paris Accord exemplify attempts to unite disparate nations around shared goals, though enforcement and compliance remain contentious. Similarly, preventing nuclear proliferation requires trust-building measures among adversarial states, challenging deeply entrenched geopolitical dynamics. Success hinges not only on technological solutions but also on fostering empathy, transparency, and mutual accountability. Reflecting on these risks also invites introspection about human nature. Why do we consistently underestimate low-probability, high-impact events? Cognitive biases play a significant role, steering attention toward immediate, tangible threats while discounting abstract, distant ones. Additionally, psychological denial serves as a coping mechanism, shielding individuals from paralyzing anxiety. Overcoming these tendencies necessitates cultivating a long-term mindset, wherein future generations receive equal consideration alongside present interests. Education, storytelling, and experiential learning can help bridge this gap, instilling a sense of stewardship for the planet and its inhabitants. Ultimately, confronting global catastrophic risks compels us to redefine what constitutes meaningful progress. Economic growth, technological advancement, and military dominance pale in significance when weighed against the survival of humanity itself. Prioritizing existential security requires reimagining priorities, reallocating resources, and embracing humility in the face of uncertainty. It also demands acknowledging our limitations. Not every risk can be eliminated, but striving nonetheless to build a safer, more equitable world. While external threats endanger us, internal flaws may prove deadlier. Let's explore the darker sides of human nature through the lens of social collapse. Having examined the myriad ways external forces threaten humanity's survival, we now turn inward to consider vulnerabilities rooted in human behavior itself. Social collapse, whether triggered by inequality, corruption, or systemic failures, reveals the fragility of the structures binding societies together. From ancient civilizations crumbling under their own weight to modern states teetering on the edge of chaos, history provides ample evidence of how internal strife can undermine even the most advanced cultures. So let us leave behind the realm of cosmic and technological perils and step into the shadowy corridors of human frailty, where greed, division, and short-sightedness sow the seeds of ruin. Social collapse, the fragility of order. Civilizations rise and fall, but what triggers their decline? Corruption, inequality, resource scarcity, all play roles in the unraveling of order. Imagine standing amidst the ruins of an ancient city, its once majestic structures now reduced to crumbling stone and overgrown vegetation. This silent testament to human ambition serves as a haunting reminder. No society, no matter how powerful or advanced, is immune to collapse. History is replete with examples of civilizations that soared to greatness only to succumb to internal decay, external pressures, or a combination of both. From the grandeur of Rome to the isolation of Easter Island, these stories share common threads, patterns of hubris, mismanagement, and environmental neglect that ultimately led to their downfall. The fragility of social order becomes particularly evident when examining modern vulnerabilities. Political polarization, economic instability, and widening inequality threaten to erode the foundations upon which contemporary societies are built. Climate change exacerbates resource scarcity, fueling conflicts over water, food, and land. Technological advancements, while transformative, also introduce new risks, from cyberattacks on critical infrastructure to the erosion of privacy and trust. As we navigate this precarious landscape, it is worth asking, are we learning from the mistakes of the past, or are we doomed to repeat them? By exploring the dynamics of social collapse, we gain insight into the delicate balance required to sustain complex systems. We also confront uncomfortable truths about human nature, the greed, short-sightedness, and tribalism that often undermine collective well-being. Yet within this exploration lies a glimmer of hope. Understanding the causes of collapse empowers us to build resilience, fostering communities capable of enduring adversity. Let us delve into this somber yet To fully comprehend the mechanisms behind social collapse, we must first examine historical examples where societies disintegrated under mounting pressures. Two iconic cases, the fall of the Roman Empire and the ecological devastation of Easter Island, provide valuable insights into the fragility of human systems. The Roman Empire, once the epitome of power and sophistication, began its decline due to a confluence of factors. Overexpansion stretched military resources thin, leaving borders vulnerable to invasions by barbarian tribes. Economic instability, fueled by rampant inflation and reliance on slave labor, weakened the empire's fiscal foundation. Meanwhile, political corruption and infighting fragmented leadership, rendering governance ineffective. Environmental degradation further compounded these issues. Deforestation and soil depletion undermined agricultural productivity, exacerbating food shortages and rural unrest. By the time Rome fell in 476 CE, centuries of incremental failures had culminated in irreversible collapse. Easter Island presents a starkly different yet equally instructive example. Isolated in the Pacific Ocean, the Rapa Nui people thrived for centuries, constructing the iconic Moai statues that symbolized their cultural achievements. However, unsustainable practices, including rampant deforestation to transport the massive stone figures, led to ecological catastrophe. Without trees to stabilize the soil, erosion rendered agriculture impossible. Resource scarcity sparked violent conflict among clans, leading to societal breakdown. By the time European explorers arrived in the 18th century, the population had dwindled dramatically, and much of the island's natural wealth was irreparably lost. These historical collapses resonate eerily with modern vulnerabilities. Political polarization, for instance, mirrors the factionalism that destabilized Rome. In many nations today, ideological divides hinder cooperation, paralyzing governments and eroding public trust. Economic instability echoes the financial crises that plagued ancient empires, with global recessions and income inequality threatening social cohesion. Meanwhile, climate change looms as a pervasive threat, reminiscent of the environmental degradation that contributed to both Rome's and Easter Island's demise. Jared Diamond's seminal work Collapse: How Societies Choose to Fail or Succeed provides a framework for analyzing these patterns. Diamond identifies 5 key factors that contribute to societal failure: environmental damage, climate change, hostile neighbors, trade partners collapse, and a society's response to its problems. Crucially, he emphasizes the role of decision-making in determining outcomes. Societies that recognize impending crises and adapt accordingly stand a better chance of survival, while those that ignore warning signs or fail to act decisively face ruin. This dynamic underscores the importance of foresight, flexibility, and collective action in averting disaster. Parallels between past and present extend beyond specific events to broader systemic trends. For example, technological innovation, though beneficial, can create unintended consequences. Social media platforms, designed to connect people, have instead amplified misinformation, deepened divisions, and facilitated mass surveillance. Similarly, automation and artificial intelligence, while boosting productivity, risk displacing millions of workers, potentially triggering widespread unemployment and social unrest. These dual-edged tools highlight the complexity of managing progress without sowing the seeds of collapse. Moreover, globalization introduces unique challenges. While interdependence fosters prosperity, it also increases susceptibility to cascading failures. A financial crisis in one region can ripple across continents, destabilizing economies worldwide. Pandemics, too, exploit interconnectedness, spreading rapidly through travel networks and overwhelming healthcare systems. Such phenomena underscore the interconnected nature of modern civilization, where local disruptions can escalate into global catastrophes. Ultimately, the study of social collapse reveals not just the fragility of order, but also the resilience embedded within human societies. Communities have historically demonstrated remarkable capacity to adapt, rebuild, and innovate in the face of adversity. Whether through grassroots movements, institutional reforms, or cultural shifts, humans possess the agency to mitigate risks and forge paths toward renewal. Recognizing this potential is crucial as we grapple with the uncertainties of our own era. The implications of social collapse stretch far beyond the immediate chaos of crumbling institutions and disrupted lives. They challenge us to reflect on humanity's trajectory, questioning whether we are destined to perpetuate cycles of destruction or capable of transcending them. At stake is not merely the survival of individual societies but the continuity of civilization itself, a fragile construct sustained by cooperation, shared values, and mutual accountability. One pressing implication is the specter of future collapses driven by climate change and technological disruption. Rising temperatures, shifting weather patterns, and rising sea levels pose existential threats to coastal cities, agricultural regions, and biodiversity hotspots. Displacement of populations, loss of arable land, and competition for dwindling resources could ignite conflicts reminiscent of those that hastened Rome's fall. Similarly, technological advancements, while promising unprecedented opportunities, carry inherent dangers. Cyberattacks targeting critical infrastructure, such as power grids or financial systems, could cripple entire nations overnight. Autonomous weapon systems, if left unchecked, might escalate geopolitical tensions beyond human control. Together, these forces form a volatile cocktail, testing the limits of societal resilience. Another critical consideration is whether humanity learns from history or repeats its mistakes endlessly. Despite abundant evidence of past failures, many societies continue to prioritize short-term gains over long-term sustainability. Deforestation, overfishing, and fossil fuel extraction persist despite clear warnings of their consequences. Political leaders often exploit fear and division rather than fostering unity and collaboration. Even well-intentioned reforms frequently falter under pressure from entrenched interests or public apathy. This pattern raises troubling questions. Are we hardwired for self-destruction, unable to resist impulses toward greed and exploitation? Or do structural barriers, economic incentives, cultural norms, cognitive biases, prevent meaningful change? Reflecting on resilience versus resignation offers a nuanced perspective. Resilience entails more than mere survival. It involves adapting to changing circumstances while preserving core values and aspirations. Communities that embrace diversity, inclusivity, and participatory governance tend to weather crises more effectively than those mired in rigidity and exclusion. Grassroots initiatives, such as community gardens, renewable energy cooperatives, and mutual aid networks, demonstrate how localized efforts can foster solidarity and self-reliance. Conversely, resignation reflects a defeatist mindset, accepting collapse as inevitable and abandoning efforts to mitigate harm. Striking a balance between pragmatism and optimism is essential, acknowledging the gravity of risks while nurturing hope for transformation. Ethical dimensions further complicate the discourse around social collapse. Who bears responsibility for preventing or responding to such disasters? Wealthy nations, having contributed disproportionately to environmental degradation, face moral obligations to assist poorer countries bearing the brunt of climate impacts. Similarly, corporations profiting from extractive industries must reckon with their role in perpetuating systemic inequities. Addressing these disparities requires not only technical solutions but also profound shifts in values and priorities. Compassion, equity, and stewardship must replace greed, hierarchy, and short-sightedness if we are to navigate the perils ahead. Ultimately, contemplating social collapse invites introspection about human purpose and legacy. What kind of world do we wish to leave behind? Is survival sufficient, or should we strive for flourishing, ensuring that future generations inherit a planet rich in beauty, opportunity, and meaning? These questions transcend policy debates, touching the very essence of what it means to be human. By engaging deeply with these issues, we affirm our commitment to building a better future, not out of obligation, but out of love for life itself. Societies crumble, but individuals endure, at least for a time. In our final segment, let's return to the personal scale and confront the ultimate nightmare, the inevitability of death. Having examined the macroscopic forces that threaten societal stability, we now shift our focus inward to the most intimate and universal experience of all, mortality. While civilizations rise and fall, each individual faces the certainty of their own end. Death, though inevitable, remains a source of profound mystery and contemplation. It shapes how we live, love, and find meaning in a transient existence. So let us leave behind the grand narratives of history and step into the quiet solitude of personal reflection, confronting the ultimate question that unites us all: what does it mean to face the end, and what wisdom might we glean from doing so? Mortality, the final nightmare. Death is the one certainty in life, yet it terrifies us most. Why does the end of existence haunt us so deeply? Few topics evoke as much fear, fascination, and reflection as mortality. Death is an undeniable truth woven into the fabric of existence, yet its inevitability often feels like a cruel paradox. On one hand, it is universal, a shared destiny that unites every living being across time and space. On the other, it is intensely personal, confronting each individual with questions about legacy, purpose, and the unknown beyond. For many, death represents the ultimate nightmare, the cessation of consciousness, the dissolution of identity, and the severing of connections to loved ones and the world. Despite, or perhaps because of, its universality, humanity has long grappled with ways to make sense of death. Cultures throughout history have crafted rituals, myths, and philosophies to confront this great unknown. Some view death as a natural part of life cycle, while others see it as a doorway to another realm. Yet, regardless of perspective, the specter of mortality looms large, shaping how we live, love, and find meaning in a finite existence. It forces us to ask profound questions. What happens after we die? How should we spend our fleeting time on Earth? And why does the thought of non-existence provoke such visceral unease? As we delve into this final segment, let us approach the subject of mortality not with dread but with curiosity. By exploring cultural attitudes, philosophical insights, and emotional responses to death, we may uncover deeper truths about what it means to be human, and discover solace in the very impermanence that haunts us. To understand why mortality resonates so profoundly, we must first examine how different cultures and thinkers have approached the concept of death. Across societies, attitudes toward mortality range from fear and denial to acceptance and reverence. These perspectives are shaped by religious beliefs, philosophical traditions, artistic expressions, and collective experiences, offering a rich tapestry of interpretations. In many Western cultures, death is often viewed with apprehension, seen as an adversary to be delayed or defeated. Modern medicine reflects this mindset, striving relentlessly to extend life expectancy and combat aging. This preoccupation with longevity stems partly from Enlightenment ideals that celebrate human agency and progress, framing death as an obstacle to overcome rather than an intrinsic aspect of existence. However, this focus can also foster anxiety, as individuals struggle to reconcile their desire for immortality with the reality of biological limits. By contrast, Eastern philosophies like Buddhism and Taoism emphasize impermanence as a fundamental truth of life. In these traditions, death is neither feared nor glorified but understood as a natural transition within the cycle of birth, death, and rebirth. Practices such as meditation encourage practitioners to cultivate awareness of mortality, using it as a tool for spiritual growth and detachment from material attachments. Similarly, indigenous cultures around the world often honor death through ceremonies and storytelling, viewing ancestors as integral members of the community whose wisdom guides future generations. Near-death experiences, NDEs, provide another lens through which to explore mortality. These phenomena, reported by individuals who have come close to dying, often involve vivid sensations of floating outside the body, encountering light, or communing with deceased loved ones. While skeptics attribute NDEs to neurological processes triggered during extreme stress, others interpret them as glimpses of an afterlife or higher consciousness. Regardless of their origin, these accounts highlight humanity's enduring fascination with what lies beyond the veil of death. Grief, too, occupies a central role in the human experience of mortality. The loss of someone dear evokes a complex array of emotions: sadness, anger, guilt, and longing, all of which underscore the depth of our connections to others. Elizabeth Kubler-Ross's seminal work on the 5 stages of grief, denial, anger, bargaining, depression, and acceptance, provides a framework for understanding how people navigate bereavement. Yet grief is not linear. It ebbs and flows unpredictably, reflecting the non-linear nature of healing. Through mourning, we confront not only the absence of the departed, but also our own vulnerability to loss. Legacy building emerges as another response to mortality, serving as both a coping mechanism and a testament to human creativity. Whether through art, science, philanthropy, or familial bonds, individuals strive to leave behind something enduring, a mark upon the world that transcends their physical presence. Philosophers like Martin Heidegger explored this impulse in his concept of being toward death, arguing that awareness of mortality compels humans to create meaning in an otherwise indifferent universe. Emily Dickinson captured this sentiment poignantly in her poetry, writing lines such as, "Because I could not stop for death, he kindly stopped for me." Her works remind us that mortality is not merely an endpoint but a catalyst for introspection and expression. Ultimately, cultural attitudes toward death reveal as much about how we perceive life as they do about our fears of its conclusion. By examining these varied perspectives, we gain insight into the myriad ways humanity seeks to wrestle with, and sometimes embrace, the inevitability of mortality. Confronting mortality shapes how we construct meaning in a transient existence. It forces us to grapple with existential questions that lie at the heart of human experience. What is the purpose of life if it ends? How do we reconcile the brevity of our time with the infinite possibilities before us? And what does it mean to live authentically when faced with the certainty of death? Philosophers have long debated these issues, offering contrasting views on the relationship between mortality and meaning-making. Existentialists like Jean-Paul Sartre and Albert Camus argued that life's lack of inherent purpose renders individual choices all the more significant. In the face of absurdity, the tension between humanity's search for meaning and the universe's indifference, they urged individuals to forge their own paths, creating value through action and authenticity. For them, mortality was not a barrier to fulfillment but a reminder to seize the moment. Heidegger took a slightly different approach, emphasizing the importance of authentic being toward death. He believed that acknowledging mortality allows individuals to break free from societal expectations and live deliberately, prioritizing what truly matters over superficial pursuits. This notion resonates deeply in contemporary discussions about work-life balance, environmental stewardship, and mental health. When confronted with the fragility of life, people often reassess their priorities, seeking fulfillment in relationships, passions, and contributions to society. Yet, some argue that mortality itself undermines any attempt to derive lasting meaning. If everything eventually fades into oblivion, does effort hold significance? This nihilistic perspective challenges us to consider whether meaning is inherently subjective or whether it requires permanence to be meaningful. The tension between these viewpoints mirrors broader debates about human potential and limitation, inviting reflection on what constitutes a worthwhile life. The question of immortality further complicates these deliberations. Would eternal life alleviate suffering or exacerbate existential dread? Proponents of immortality envision a utopia where knowledge accumulates endlessly, diseases vanish, and humanity achieves unparalleled heights of creativity and exploration. However, critics warn of unforeseen consequences. Eternal life could lead to stagnation, boredom, or even despair as individuals grow weary of endless repetition. Moreover, the pursuit of immortality risks diverting resources away from addressing pressing global issues, perpetuating inequality and neglecting those currently suffering. Art and literature offer poignant meditations on these themes. Poets like Emily Dickinson and philosophers like Friedrich Nietzsche remind us that mortality imbues life with urgency and beauty. Dickinson's imagery of death as a carriage ride suggests acceptance tinged with wonder, while Nietzsche's proclamation that eternal recurrence demands we live each moment as though it will repeat infinitely underscores the weight of our choices. Both perspectives affirm that mortality, far from diminishing life, amplifies its significance. On a practical level, Confronting mortality fosters resilience and empathy. Shared vulnerability reminds us of our interconnectedness, prompting acts of kindness, compassion, and solidarity. Movements advocating for palliative care, mental health awareness, and environmental preservation reflect collective efforts to address the anxieties and injustices associated with mortality. By embracing impermanence, we cultivate gratitude for the present and responsibility toward the future. Ultimately, mortality invites us to embrace paradoxes: joy amidst sorrow, connection amid separation, and creation despite destruction. It is both terrifying and beautiful, tragic and liberating. Rather than resisting its inevitability, we might learn to cherish the fleeting moments that compose our lives, finding solace in the shared journey toward the unknown. Thank you for joining me on this journey through existential nightmares. Remember, while these thoughts may unsettle, they also remind us of the beauty and mystery of existence. Sleep well and dream wisely. As we conclude this exploration of mortality, let us carry forward the lessons gleaned from confronting life's greatest uncertainty. Death, though daunting, is not merely an ending. It is a mirror reflecting the values, hopes, and dreams that define us. By acknowledging our finitude, we awaken to the preciousness of each breath, each encounter, and each opportunity to shape the world around us. In doing so, we transform the terror of mortality into a source of inspiration, courage, and connection. May this reflection guide you gently into rest, where dreams weave stories untethered by the constraints of waking life. Good night, and may your sleep be peaceful.